Now that we've had a chance to dig into the basic binary and hexadecimal numbering concepts, we're now going to lead into how we actually apply these numbers and what they work towards. In dealing with this, we have to understand that the binary digits have meaning, and in having meaning, it begins with something as simple as looking at a lantern. Since a lantern does nothing but have a light that turns on and off, the absence of light would be equivalent to looking at a 0, just like having light would flicker on and give the presence of a 1, or a binary 1, on, as a state. When the light turns off, it shifts off where someone had seen the 1 and now sees a 0 state, which is off. If we were to turn this light back on one more time, that would have sent Paul Revere on his magic ride that night. In other words, the bits have meaning. Oneth by land, twoeth by sea. Here he saw the light turn on once, twice, which meant that it's by sea. If it would have only been on once, it would have been by land. So he saw the 1, the light turn on, the absence of light, and then saw the 1 flicker on again, which had meaning, which sent him off to deliver a message. Moving forward into time, we actually did something a little bit less sophisticated. What we did was we would take a document, give it to a person who used a teletype to flick on and off, which sent a series of 1s and 0s across a wire, where a gentleman on the other end of the wire would take that information and cut it off the printer to reproduce the document. As you can see here, it's the same concept, but done a different way. Using it in today's terms, we could actually take a document from the internet or from your favorite website, which is known as the cloud. When we go to download the document, technically, we download that document in 1s and 0s, where that information is reproduced on our local computer and reveals the document again. These concepts will be used much more in the application of 1s and 0s as we move forward with this lesson. As we apply that basic concept toward hardware, we'd like to see that the first device here, which is a cable, and a connector on the top of it would have a name for us. That's actually a Category 5 cable, which is also can be unshielded or shielded twisted pair. And when looking at Category 5 cable, the Category 5 cable is designated a category by the number of twists per inch in the cable to try to eliminate the effects of electromagnetic impulse. So we have a unshielded twisted pair, or UTP or STP Category 5 cable with a jack or registered jack type 45 or an RJ45. This cable and connector would then plug into a device on your computer that would look something like this, which we call a network interface card, or NIC for short. When showing the pins in a much larger view, we could see that an RJ45 would have pins on it. It also has a place where the cables connect up through. Now if we were to take an RJ45 on one side and connect it to another RJ45 on the other side through a Category 5 cable, we see that the cables could not be painted black as we have here, because in looking at it a little bit closer, the pins are numbered 1 to 8 when looking at the clip face down. The other cable would also have pins 1 through 8. When trying to figure out which pin connected to the pin on the other side, it would be almost impossible to find out if all the colors were indeed black. You would need to put a device called a toner on either end to trace out where one pin terminated on the other. So instead, we used a standard mechanism to identify them. The first way to standardize the cabling would be called what is called a T568a standard. In this case, the cables are colored green, white, green on pin 1 and 2, orange, white, orange on pin 3s and 6 respectively, blue, blue, white on pins 4 and 5, and brown, white, brown on pins 7 and 8. As you can see here, it really is a striped cable solid color pattern. In this case, green, white, green, orange, white, blue, blue, white, orange, brown, white, brown. There was also another standard that we implemented, which is called T568b. In this case, we use the same colored cables, except we swap pins 1 and 2 with pins 3 and 6. Therefore, the orange, white, orange cable would come first, and the green, white, green pair would take the place of where the orange, white, orange pair was with T568A. When implementing the standard in connecting devices, it's really all about which pins we're trying to communicate on. So when looking at these types of cables, looking at the top cable first, we'll notice we're looking at pins 1 through 8 on one of those NICs on one of the devices to pins 1 and 8 on a NIC on a completely different device. So when looking at a network interface card connected to a computer, the receive is on pins 1 and 2 on a PC, but if we were to look at it on a device called a switch, which a PC would normally connect up to, you see how pins 1 and 2 would be the transmit. Inversely so, pins 3 and 6 are transmit on the left-hand side with the PC, but are receive for the switch side. Therefore, if we had T568B on both ends or T568A on both ends, pin 1 would go to the other pin 1 on the other side, pin 2 would go to the other pin 2 on the other side. Therefore, if they are unlike devices, receive would go to transmit, transmit would go to receive, and communication would be possible. That would be called a straight-through cable. But when connecting a cable up to two like devices, we cannot connect 1 to 1, 2 to 2 as we did before, because the internal pinouts are identical. Therefore, we must swap pins 1 and 3 by using T568B on one side and T568A on the other. The receive pins would be on the same pins. The transmit would be on the same pins. Therefore, 1 would technically go to 3 on the other side, which would be receive to transmit. 2 would go to 6. 3 would go to 1. And 6 would go to pin 2 on the other side. And this is the way we would have receive to transmit, transmit to receive. Therefore, when we use like devices, we use a cable called a crossover, which is easily explained by how the cables cross over each other. When connecting a device directly to a console port of a router or to a switch or to a network device, we normally go from a serial port or a USB port on a PC that would connect to the console port of the device. When trying to communicate or initially configure it, we would need a special cable called a rollover. And the rollover cable would be pins 1 to 8, 2 to 7, 3 to 6, and so forth. In order to explain where the desire of networking came from, it would start with the basic model of using a printer with two computers. If one computer wanted to use the printer, he would have to be connected. If the other computer needed to be connected to the printer, you would have to disconnect the cable and reconnect with the other device. And then if the other person inversely said, I need to use the printer, you'd have to disconnect and reconnect again. As we can see, this process is very manual and is not really conducive to cost, because in order to have someone dedicated to their own printer would be very expensive. Therefore, we began to network this out by using what was called Rg6, or a thick net cable. This is actually a piece of copper wire which is fairly thick. You would have a connector that would clamp onto the wire, have another cable that would connect off and be connected into the computer. The good news about this is you'd have everybody on the same wire, therefore everyone would be able to reach the printer. The bad news is if you wanted to easily connect somebody to the cable, it would be arduous, and only so many devices would be able to fit on that wire. When moving a little bit further, we started to use thin net or Rg59 cable, which is also a very similar cable that you would use with your cable at home for cable television. And for this type of cable, we used what was called a bullet or a BNC bullet that would connect either ends of the wire into both sides of the cable, and the computer would come off the single tap in the middle. Either way, this was the basic infancy of networking. So what we needed to do is, instead of being able to cut the wire to add a computer to the device one at a time, because if we cut it, obviously the network would go down in order to put one of these BNC Ts or BNC bullets in place, it would take it down, and that would make a lot of people unhappy. Therefore, what they did was we would put that same cable, that same black cable, into a box, and that box would be called a hub. You'll notice here on the hub, it's got the Rg59 receptacles on the ends, which would make it very easy to have someone plug into it and unplug in without taking the network down. When trying to figure out how a hub would work, as each device is plugged into the hub, if someone were trying to get into the printer, it would go across that same black wire. As long as everyone heard the bits on the wire, they would all hear it and therefore not transmit. Because the rule is, as long as you hear someone talking, you're not supposed to talk on the wire. The problem comes in when one person needs to print, represented by the red ones and zeros, and another person did not hear him in time by the time he started transmitting the ones and zeros, which means their ones and zeros get intermingled on the wire and the data becomes corrupted. So the fancy way of explaining this is a collision would take place on the wire. When describing collisions on a hub, we would say that if everyone had access to the same wire at the same time, and if everybody would talk, a collision would take place, we would say that this would be called one collision domain. Therefore, a hub only has one collision domain. And in order to handle the collisions, we'd have to run a protocol across the hub called carrier sense, because it would sense the carriers on the link, multi-access, because everyone has access to the same wire, and collision detect, because it would actually detect the collision. Fancy way of saying this protocol would be CSMA/CD. Now, when running this protocol across the wire, it would actually send a jamming signal in both ends back to both of the hosts to tell them to pretty much be quiet and not say anything on the wire. Both of those hosts would set an internal timer that hopefully was not set to the same decrementing value. And once your value decremented to 0, you can then begin to transmit on the wire. The issue is while they are not transmitting, other people can transmit on that wire. And usually when somebody would talk again, everybody else would hear it and not talk. The problem is, the more people you plug into the hub, the more chances you can have a collision. When examining a switch, which replaced the hub, you'll notice how the printer is plugged into a port, looks like an Rg45, and so are the hosts or the PCs. The only issue is each of these devices on a switch are plugged into their own application-specific integrated circuit, or ASIC. So they don't really share the same black wire. In fact, all those ASICs are then plugged into a matrix to make sure that none of them can really collide with each other. Therefore, everyone is in a different collision domain. In fact, the number of ports on a switch defines how many collision domains you have. Therefore, we don't have that same problem as we did with hubs. Now, the back part of a switch hardware is, just to apply some of the things you've learned so far, is you would actually connect a cable to it that had an RJ45 on the end that plugged into a serial port on the back of your laptop or computer, and we would use a rollover cable to initially configure it or connect to it. Placement 2 is where the exhaust would come out, or the warm air, because it is a computer and it does run electronics there. Things tend to get warm, and that's where the exhaust would come out. 3 would be used, the 3 slot there would be used for redundant power supplies if you need them. And 4 is where you'd plug the AC plug into on the back of this 2960 switch. On the front side, you would see a number of RJ45 receptacles, which is usually defined by the switch type. So if this were a 2924, there would be 24 ports that you could use for hosts. A 2948 would have 40 or 48 ports, which was what we see here. That's where you would connect the host to, or the printers. But in order to expand, because normally in a closet you have a lot more hosts to connect into than the 48 ports would encompass, you'd normally have uplink ports all the way furthest to the right that would connect to other switches, and then those switches would be connected to other hosts, or a printer in this case. So when defining connectivity, Switches plug into hosts or computers. The switches are interconnected through uplinks. And the definition of a switch connected to other switches, connected to hosts, we use a fancy term called a local area network, or a LAN. A router is another device or another computer that could be used to move packets across the internet. In here we have a 2900 series Cisco router. As you can see on the top portion there, the front panel is quite boring, only because all you have is a power switch and a power receptacle. But if we look at the back side, which is where all the magic happens, this is where you determine the connectivity of the router. And when breaking out the connectivity of the router, some things we could point out there are ports there where your computer can connect up to initially configure it through what's called the console port, very similar to what we saw on the switch. There are other ports, as we're pointing to here, where you can connect a modulator demodulator or modem, where you can dial into the device through a telephone line. Other ports would be things like where fiber optic cable can connect it to. In this case, we have what's called a LC connector, and the module to the right there is called a small factorable plug, or SFP, that cable plugs into. Other termination points would also be an RJ45 with category 5 cable. As you can see, we have a number of terminations on the router. We also have slots, and the slots are normally labeled 0 all the way furthest to the right and down, and then slot 1 to the left, and they're usually numbered right to left, bottom to top. It's not always the case, but in most cases that is what it is. So we have some slots that are used for what are called, in this case, a high density WAN interface card that we use to connect up to the wide area network. As you can see, there are 4 little mini slots that are used to connect with high density WICs. We also have the bottom slots that could be used to plug in little switches. So as you can see, these 2900 routers, in this case a 2921, because it has 2 major large slots on the bottom which to plug these cards into. A router, you can actually plug in hard drives into those, or other wide area networking ports. So as you can see, a router is very useful with connectivity, and normally it will translate medium from, say, one type of medium to another. So when looking at this from a generic perspective, you'll notice how you have switches. Regardless of how many switches are connected through their uplinks with the host, we still only have one local area network. And this normally, if everyone's sitting there trying to talk, and someone actually yells out what is called a broadcast, where you send one message and multiple people hear it at the same time, there's only one broadcast domain within a local area network. So if one of those hosts sends a message that's broadcasted out, everyone would hear it. Therefore, there is a need to separate the local area networks. So in this case, I don't want to use a bunch of switches within one local area network. Instead, I'll isolate them, and we use a router to interconnect them. So technically, a local area network is also equivalent to a broadcast domain. So a router is used to separate those broadcast domains. And normally in the internet, routers are connected to other routers. And that connection between the two routers would be like its own LAN. And that bottom router would then be connected to other LANs. So in reviewing the physical connectivity, if we were trying to connect that computer at the top to the computer at the bottom, the normal progression would be a computer's network interface card connected with an RJ45 connector into it, category 5 cable that would span across to another RJ45 connector that would plug directly into a switch. This cable, since it is a natural progression flow, would normally be a straight through cable. If you're connecting a switch normally plugs into a router or terminates to a router, which means everything connected to the switch is in the same local area network, and the router isolates that local area network off its port. Routers would then be plugged into other routers. In this case, if we plugged one router into another, we'd normally have what's called a crossover cable to connect them. However, nowadays we actually have the electronics can automatically change the pinouts internally so that a straight through cable can actually be used. And that router would then be connected to another switch. That switch would be connected to a NIC via a category 5 cable and another RJ45 termination to it. And that would be the review of the progression of flow of data. So when looking at it from a very large scope, you'll notice the switch to the left is connected to computers or a PC or a laptop that's plugged into it, that gets plugged into a router, into another router, onto a different LAN that has more computers and more laptops. So when looking at this from a diagram perspective, it would look something like this. Hosts connect to switches, switches connect to routers, routers then normally connect to other routers through the internet. A router eventually will terminate to another switch, and that switch is connected to a different set of hosts.